At the exact moment that physical activity begins, skeletal muscles undergo immediate microscopic stress as they generate force. Muscle tissue only stores enough localized adenosine triphosphate, or ATP, the primary energy currency of the cell, to last 0 to 10 seconds during maximal explosive output. Once that initial ATP is depleted, the body faces a physiological crisis. To avoid muscle failure, it must instantly synthesize new energy to meet the rapid turnover of ATP. In the metabolic background, 3 potential dietary fuel sources wait to be utilized: carbohydrates, proteins, and fats. Unlike a mechanical engine, the human body cannot rely on a single, static fuel tank to survive varying levels of physical stress. Survival requires metabolic flexibility, the ability of the biological engine to adjust its substrate utilization in response to varying exercise demands. This flexibility is governed by 3 primary factors: exercise intensity, duration, and the availability of oxygen. The constantly shifting ratio between burning fat and burning carbohydrates is dictated by a threshold known as the crossover effect. Mastering this biochemical math provides a necessary framework to predict endurance limits and optimize nutritional planning, alongside other metrics like VO2 max and lactate threshold. During low-intensity exercise, the body operates at an oxidative baseline where it has ample oxygen and time to metabolize fuel. This diagram illustrates the architecture of energy production. On the right, the oxidative system provides long-duration energy for several minutes to hours of activity. In this aerobic state, fat serves as the predominant and most efficient fuel source for sustained energy. Fat utilization begins with lipolysis. As shown here, triglycerides stored in adipose tissue are broken down into free fatty acids. These acids are transported to the working muscle, entering the mitochondria. Here, they undergo beta oxidation to drive ATP synthesis. While fat oxidation yields a massive amount of total energy, the multi-step biochemical process is slow compared to carbohydrate metabolism. Hormonal regulators like adrenaline and cortisol facilitate this process, maintaining low insulin levels to mobilize fat from stores. Fat is a dense fuel for a marathon, but its slow processing speed renders it inadequate for a sudden sprint or heavy lift. As the physical exercise intensity suddenly increases, the mechanical demand for ATP outpaces the slow speed of fat oxidation. The body must immediately recruit the glycolytic system, shifting its reliance away from fat and toward carbohydrates. Glycolysis occurs rapidly in the cytosol. During high-intensity bursts, it can function anaerobically by converting pyruvate to lactate to sustain energy production. This graph plots the mathematical relationship between exercise intensity and macronutrient energy contribution. At low intensity, fat provides 65% of energy, but as the intensity rises to high levels, its contribution drops to just 15%. Simultaneously, carbohydrate reliance surges from 30% to 80% to meet the rapid demand for ATP. The intersection of these 2 lines is the crossover effect, the tipping point where the body switches from fat-dominant to carbohydrate-dominant metabolism. Protein remains a minor contributor throughout this shift, providing a flat 5% of energy expenditure across various intensities. Branched-chain amino acids, or BCAAs, are primarily used for muscle repair and mTOR signaling, a pathway that stimulates protein synthesis. They are only used for gluconeogenesis, or the creation of glucose, if glycogen stores are depleted. Once an athlete crosses this metabolic threshold, their performance is limited by their internal stores of carbohydrates. To sustain the drain of high-intensity glycolysis, muscle and liver glycogen stores must be constantly replenished. Not all ingested carbohydrates are biochemically equal. Their utility depends on their digesting kinetics and the gastrointestinal tract. Complex starches are broken down by the enzyme amylase, while simpler sugars reach the bloodstream rapidly. The glycemic index, or GI, measures the speed of this blood glucose response. GI alone is an incomplete metric for athletes because it measures speed but ignores the actual mass of the fuel being ingested. As shown in this equation, the glycemic load, or GL, provides a more accurate predictive metric by correcting the GI for serving size. Watermelon has a high GI, but its GL is very low because it is mostly water, delivering very little actual fuel to the muscle. Manipulating the glycemic load allows sports dietitians to align the delivery of systemic ATP with specific windows of metabolic demand. Effective fueling requires calculating the rate of glycolytic drain against the precise glycemic load of the dietary intake. The metabolic math of the human body isn't static. Chronic endurance training triggers physical adaptations at the cellular level, changing exactly how the body processes fuel. Consistent, long-term training actively increases mitochondrial density and significantly enhances the activity of oxidative enzymes within the working muscle fibers. This cellular upgrade allows an athlete to process oxygen and oxidize fats at higher exercise intensities. We can return to the metabolic model to visualize how these cellular changes alter the performance data. The entire crossover intersection point shifts to the right along the x-axis. This shift spares precious glycogen reserves, allowing trained athletes to maintain high output for longer periods before hitting a performance wall. Because training alters the internal engine, dietary planning must be personalized. This table shows how macronutrient recommendations shift based on training type. Endurance athletes require high carbohydrate intake to maintain glycogen, whereas strength sports focus on higher protein ratios to support muscle repair and growth. Peak physical performance is the result of mastering the biochemical intersection of exercise demand, cellular adaptation, and calculated nutritional supply.